Hello, I'm Guillermo Bautista, and this is my final project for our 3D printing class. It's a lesson plan titled Sculptures and Shadows, Integrating Mathematics, 3D Modeling, and 3D Printing. So this is the problem for this project or lesson. A philanthropist wants a special sculpture whose shadows are on the right. So these are the shadows. If the light sources are from the top, the front, and the side. So the actual sculpture should be 20 feet high, 20 feet wide, and 20 feet long, as shown on the diagram. Your help is needed to design the sculpture. So as you can probably see, this is intended for students. So the task is to discuss with your group mates how the sculpture will look like. Make a sketch of the sculpture and use 3D modeling to model it and also print it using a 3D printer. So if you want to challenge yourself before proceeding to the video, I think this is a very interesting problem. So if you want to challenge yourself, you can just abandon the video and come back later, or maybe pause the video and try visualizing the object in 3D. Right? So this is the expected output. So the students should be able to model the 3D object whose shadows are shown here. So as you can see, if you look at the top, if you put the top on the light, if you put the light on the top, directly on the top of the object, the shadow will be a circle. And then if you put on the front side, for example, here, this will be the shadow. And when you put the light on the side, so this will be the shadow. So this is the object that we are looking for. Here, the students can, of course, model the object using any modeling software. So, of course, they can use Tinkercad, they can use GeoGebra, maybe they can use Blender or any 3D modeling software. And after that, after the students model the object and they are correct, we have to discuss the mathematics of the project. So one, what are the mathematical concepts that you used in creating the artwork? Two, what are the difficulties that you encountered in modeling the figure, in printing the figure? And how did you solve them? And three, suppose that the height and the width of the figure measure 20 centimeter on the three views. Approximately how much filament is needed if the model is printed with solid infill, printed with 15% infill, printed with 50% infill. So how much infill would you recommend and why? In creating the actual sculpture, how much materials do you think is needed? So, and the last three questions are, what materials do you think should sculptures use? The philanthropist requests that you paint the sculpture with two coats. How much paint will you need if 1 gallon can cover 350 square feet? So remember earlier that we already specified the dimensions of the sculpture. So this is 20 feet. It's all 20 feet high, 20 feet wide, and 20 feet long. And in creating the actual sculpture, how much materials do you think is needed? So, so what have you learned from these lessons? That's the last question. So these questions, I have tried to put the answers, or the expected answer, at least the possible answers, in the lesson plan. So this is the lesson plan. And in this presentation, I will try to explain why I developed those questions. So we already know this. This is a problem. So what are the mathematical and non-mathematical concepts? What are the mathematical and non-mathematical concepts that they use in modeling the solid? So I think that was the first question in the PowerPoint. Of course, they will use angles. They will use rotation. Angles is for slicing the cylinder. They will use rotation, maybe to rotate the plane about a line so that they can slice the cylinder. Linear congruence, they should be able to see that the length, the width, and the height are congruence and linking 2D and 3D. So this is more on visualization. So as you can see here, it says the discussion highlights the mathematical concepts that are learned in modeling and printing processes. It emphasizes the idea that mathematics is needed in solving real life problems. So the reason why I asked this question is because there are a lot of 3D printing projects that are just 3D printing projects. So I want to connect it more to mathematics, and maybe some teachers, can also connect it to science and other areas of STEAM. The second is, what are the difficulties you encountered in modeling the figure, in printing the figure, and how did you solve them? So the possible answers that I expect for this, I haven't tried this yet with students. So maybe using the software. Maybe some of the students don't know how to use a modeling software. In Austria, this is usually students know, but in other parts of the world, particularly in my country, so maybe some students do not know how to use even Tinkercad. So visualizing the solid, maybe the problem is difficult, and unfamiliarity with 3D printers. So of course, not all students are familiar with 3D printers. No, it's a new technology. So probably that's the possible answers that will emerge. But of course, there are probably others. So that's why it's good to try this out to students. So the discussion in this section emphasizes verbal communication. Here, we want students to communicate what their difficulties are and how they solve them. The answer should be noted by the teacher in order to address these difficulties in the next implementation. So it's always good to note when you have a lesson plan to note the answers, so that later when you implement it again, it's easier because you have anticipated all the answers. All right, so here suppose the height and the width of the cylinder measure 20 centimeters. So the original figure was 20 feet, right? But here we are reducing it to 20 centimeters because we want to relate it to 3D printing. And approximately how much filament is needed if the model is printed with solid infill, printed with 15% infill. So solid means 100%, printed with 50% infill. So this question actually connects the 3D printed object or 3D printed model with mathematics, and here it is in the context of volume. It's I created the need for them to compute the volume, not just calculate the volume without even the need. But here, the students need to compute the volume because they have to know how much filament will they need in printing the model. So of course, these are all approximates because, for example, in the 15% infill, it's probably not really 15%, maybe very close to 15%. And also we have to consider the exterior of the model, which is always solid. So for some centimeters, it's solid. So it's not always exact. So the formula, of course, is the figure is a cylinder, and it's cut into two, so diagonally. And of course, the formula for the volume is pi r squared times height, and the radius is 10 because the diameter of the cylinder is 20. So pi r squared times height, and the approximate volume is 6,280 centimeter cubed or cubic centimeters. And then since we halved it, so meaning the volume of the actual figure is half the volume of the cylinder, which is 3,140 cubic centimeters. And the 15% of that is, of course, 471, and 50% is 1,570 cubic centimeters. But then again, let me highlight that this is indeed that this is not an exact figure. This is not the exact amount of filament that will be spent, because everything, of course, is approximation. So how much infill would you recommend and why? So this is not really a very important question, but I think it has something to do with saving the filament. No? If you don't need a solid infill, then you don't have to put a solid infill, because in this figure, for example, it's a very stable figure. So you don't really need a high percentage of infill. Maybe 15% is enough. Okay. So in creating the actual sculpture, how much materials do you think is needed? So here we are just transitioning from uh, the model here to the actual um, sculpture. So if the students, again, calculated this, meaning they don't understand that the change of they don't understand similarity, because they just have to change the unit here. It's 20 centimeter, 20, and the actual sculpture is by feet, but still, but also 20 feet. So they just have to change the unit. All the calculations will be the same. Okay, so what materials do you think sculptors use? So this is more on the research part of the students. No? So maybe they don't know how our actual sculptures are made. I myself don't know. So this is an opportunity for them to research on the internet of the composition of sculptures and maybe the different materials that are used. So this one, the philanthropist requests that you paint the sculpture with 2 coats. How much paint will you need if 1 gallon can cover 350 square feet? So as you can probably see, this is more on the surface area. We want to find the surface area of the figure. And in finding the surface area, of course, we have the lateral area of the cylinder cut into half. So the lateral surface area is this area here. And the formula for that, of course, you don't need the formula, because you can just find the circumference of the cylinder and then multiply by the height. So that's 2 pi r height. But since it half the lateral area, because we cut the cylinder into 2, so just instead of 2 pi r height, it's just 2 pi r. It's just pi r height. So again, we substitute the values and we get 628 square feet. And it said that 1 square feet or 1 gallon can cover 350 square feet, which means that you have to divide the number of square foot to by 350. So here the amount of paint needed is 1.79 gallons. And since we need 2 coats, we assume that we use the same amount, but of course, in reality, it's probably less. So these are the discussions, of course. These are the nitty-gritty of the discussions when you discuss them with students. So 1.79 times 2 is 3.58. And then after that, we take the area of the ellipse. Actually, this is an ellipse. It's 45 degrees. No? And the area of the ellipse is pi PQ, where P is the length of the major axis and Q is the length of the minor axis. So here the length of the major axis can be this is a right triangle. So you can calculate the length of the major axis with the Pythagorean theorem, and the length of the major axis will be the half of this. So that's why when we calculated here, this is the Pythagorean theorem, and then the answer to this divide by 2, we have 14.14. And of course, the Q is the radius of the cylinder, which is 10. And you calculate um, uh, using the formula pi PQ, and we get this. Again, we divide this by the amount by 300 feet per gallon, and we have 1.26 gallons. And multiply by 2, we have 2.52 gallons. And we add, so the sculpture needs from here, this should be 3.58. So this should be 3.58. I haven't changed this. Plus 2.52. So that's 0. That's 5. That's 11. So 6.1. Hopefully, my addition is correct. So you can just check it, double check it. And lastly, what have you learned from this? So by the way, before I end, note that the shape is the ellipse because of the 45% cut. The angle is 45%. Oh, sorry. The angle is 45 degrees. So that's why it's an ellipse. If it's not 45 degrees, then it's not an ellipse. It's an elliptical ellipse-like shape, but it's not an ellipse. So I specifically designed the cut to be 45 degrees. Okay. So another possible misconception of the students is that they might calculate also the surface area of the bottom, but of course they don't need to calculate it because it's on the ground. So they don't have to paint it. That's why this is the only amount of paint needed. Okay, so we can ask the students after what have they learned. So they learned 3D modeling, 3D printing, applying the area and volume, applying Pythagorean theorem, linking 2D and 3D models, and linking models and real life. All right, that's it. Thank you very much.